Consider a positive point charge plus Q. We know that it creates a vector electric field that points everywhere radially away from the charge and fills all space. The point charge also sets up a scalar electric potential around the charge, and an obvious question to ask is what is the value of the potential at different points in space around the charge? Earlier we showed that the difference in potential between 2 points, say A and B, depends on the work done in moving the charge from point A to point B. Let's place a small positive test charge near a positive point charge. Because the two charges have the same sign, the test charge experiences a repulsive force and is pushed away from point A to point B. By calculating the work done to move the charge between points A and B, we can then derive an expression for the potential difference between these 2 points, which will represent the potential difference near a point charge. In general, we calculate the work as the product of the constant force along the direction of motion times the displacement. Here, the force on the test charge is along the direction of motion. However, it is not constant. Since the force is given by Coulomb's law, it depends on 1 over r squared. Thus, as the test charge is pushed away to larger r values, the force on it continuously decreases. To correctly calculate the work, we have to use calculus and integrate over the distance from point A to point B. Here is the result. This is valid whether Q is positive or negative, and whether Q naught is positive or negative. We can now substitute this expression for WAB into the equation for the potential difference. The two distances that define the location of points A and B, namely RA and RB, are arbitrary. We can let RB be at infinity. Thus, that term becomes equal to 0, and it is customary to set zero potential at infinity. And since the position of point A is also arbitrary, it is standard convention to drop the subscript and write the potential in the following form. This is how you calculate the potential at a distance r from a point charge. It does not refer to the potential in any absolute sense, but instead gives the potential difference relative to the potential at infinity, which we assume to be equal to 0. Notice that when Q is positive, the value of the potential V is also positive, and when Q is negative, the value for V is also negative. Therefore, a single point charge raises or lowers the potential at a given location depending on whether the charge is positive or negative. However, if 2 or more charges are present, then the total potential at a point in space near the charges is the scalar sum of the potentials from each of the charges. For example, let's say that 3 point charges are located on the vertices of a rectangle, as shown in the figure. We could ask, what is the potential at the empty corner at point P? If we label the charges 1, 2, and 3, then the potential at point P will be equal to the scalar sum of the potentials from each of the charges. Or, V at P will be equal to V1 at P plus V2 at P plus V3 at P. Since each of the individual potentials is due to a point charge, we can write each term as a kq over r. Thus, V1 is equal to kq1 over r1, V2 is kq2 over r2, and V3 is kq3 over r3. The distances r1, r2, and r3 represent the distance from each of the charges to point P. Based on the information in the figure, r1 equals 3 meters, r3 equals 4 meters, and r2 will be equal to the diagonal distance of the rectangle, which we can get by Pythagorean theorem. Or, r2 is equal to the square root of r1 squared plus r3 squared, which equals 5 meters. We can now calculate the total potential at point P using the charges and distances in the figure. We get the following. Notice that we have both positive and negative point charges contributing to the potential at point P, and the overall sign of the potential will depend on how much the negative and positive charges contribute, which is based not only on the magnitude of each charge, but also its distance from point P. Once we know the value of the total potential at point P, we could ask the following question. How much electrostatic potential energy would a fourth charge, Q4, have if placed at point P? We can now easily answer this question by using equation 19.3. The electrostatic potential energy would be equal to Q4 times the potential at point P, which we just calculated previously. Notice that the sign of the potential energy will depend not only on the sign of the potential at point P, but also on the sign of Q4. If Q4 is a positive charge, then its potential energy at point P in this case would be negative.